All right, everybody, welcome to my series of videos on Calculus 1. We're going to start with an introduction to limits, but in this video, actually, we're really not going to talk too much about limits, at least formally. What we want to do is start with talking about closeness. What does it mean for two things to be close to each other? Now, really what we're going to be doing is describing a small distance, where the emphasis is on small, right? Two objects are close to each other if the distance between them is small. Calculus, as a whole field in general, is concerned with only a couple of major issues, and one of them is dividing things up into really small pieces. And so we're going to try and formally talk about what it means to have a small distance. And then we'll talk about Zeno's paradox and how that can be used to kind of describe closeness or small distances. Zeno famously has three, I think, paradoxes describing how motion can't happen, which is kind of a weird idea. And we're going to focus in on one of them to just try and describe this idea of a small distance. So, a thought exercise for us. I'm going to put two objects up on the screen, and you're going to think to yourself about if these objects are close to each other. And there's really a follow-up question. The follow-up question is, what does it mean to you to be close? Or formally, what does close mean? So, two objects up on the screen. You can pause the video for a little bit to think about it. These two dots. Are these two dots close to each other? If so, why? If not, why not? Really what I'm getting at is, what's your definition of closeness? Try and formalize that in your head. Pause the video again, and we'll think about this together. All right, another thought exercise for you. I'm going to do the exact same thing, but I'm going to put the objects in different positions. And I want you to think and try and decide for yourself, yes or no, are these objects close to each other? And again, what does that really mean? What is your definition of close? Try and formally describe it. If you need to, write it down in words. These two objects would be close together if blank, some definition of closeness. So here's your next example. Are these two dots close to each other? If so, why? What does that mean? If not, how come? All right, let's talk about this. This is an example that I do every semester in class with physical objects, whether I'm standing somewhere and describing my closeness to something in the room like a door, or if I've got something drawn up on the board. But here are our two situations. Are these close? If so, how come? If not, why not? And over the course of me doing this, I've seen several different reasonings. We'll say yes, and we'll say no. This isn't me describing that these two objects are close to each other and these two aren't. These are just some reasonings that we have. Some people I've heard say things like they are within some distance. Maybe it's like a foot, right? I've heard people describe when I was standing in the front of a room by a doorway, they said, yes, you're within a city block of the doorway. That's my definition of close. If I'm downtown in the city, I'm close to something if I'm on the same block as it. And so as long as you're within a city block of that object, those two objects are close to each other. And I guess I don't really need a yes or no, because these are just kind of definitions of closeness, right? We can talk about like widths, right? We could talk about distances with regard to itself, almost like a self-referential distance. These two objects might not be close because you can fit a whole bunch of these same-sized dots in between, and these two objects might be close because you might not be able to fit, another dot in between. There are all sorts of these kinds of standards. If we're using people, sometimes they'll say, like, if you're within an arm's length of something, you're close. But if you can't reach out and touch it, you're not close. I've heard people have really, really stringent standards of closeness. Within here, I heard one person, one semester, one student say, you have to be within an inch of some object to be considered close. And you probably have some sort of a definition for what it means to be close to something. maybe that definition is an overlap with somebody else's. Maybe you were like, yeah, it is within 1 foot of distance. Maybe you could say they're on the same screen. I can view them both at the same time on my computer monitor. That's close. There's all these different types of things. But the thing that we should notice is that these definitions of closeness are all purely subjective. We can all have differing definitions of what it means for two objects to be close to each other. And what that means is that it is impossible for us to classify these objects as close or not close with universal agreement, right? There's no way that we can all come to a decision on this. And I'm assuming when I say all, I'm talking about maybe like an infinite number of people, right? If we all have some subjective definition of closeness, it's going to be at the very least really difficult for us to come up with two objects that are within some sort of a distance, like these ones that we've got, where we can all agree and say, yes, those are close to each other. So let's take that thought exercise. What if we did all agree that we're allowed to hold different definitions of close, but we have a different definition, a different term, arbitrarily close, and that means that we could come up with some objects that are close enough to each other that they meet every standard of closeness that anyone could possibly have. They're within some distance where everyone is going to look at them and say, yes, that meets my definition of what close means. Whether that definition is within a foot or an inch or some self-referential definition about if you can fit an object in between them or if you're within an arm's length or something else. For every arbitrary definition of closeness, the two objects that we're thinking of are arbitrarily close if everyone could agree. Now, hopefully, that's a bit of a mind-boggling, maybe not even realistic situation. It's hard to think of how close you would need to be to beat everybody's minimum standard of what it means for two objects to be close to each other. This is feeling almost like a philosophy instead of a math class, right? All right, so let's talk about Zeno's paradox. More philosophy here. Zeno has a bunch of paradoxes, and this one is probably my favorite to show to people because it shows up in so many different contexts. So let's say we have some sort of a student and a doorway. Maybe the student is graduating, and so they're looking to leave the school because they're going on to bigger and better things, and they're going to walk towards the doorway. Zeno famously said that you'll never actually get there. Well, that's weird. But Zeno's idea was that if we're going to go through this distance from the student to the doorway, the student has to go half the distance first. And then after that, the student has to go another half the distance. And then after that, the student has to go another half the distance. And what we'll notice is that if we kind of zoom in on this, or what I'm going to do is I'm going to get rid of the picture of the student, and I'm just going to put a little tick mark there. If we keep just taking steps by moving half of the remaining distance over and over and over again, we'll never actually get to the doorway. So let's get rid of the person and put a little tick mark here, and let's watch this tick mark move along. It's going to go half the remaining distance, and it's going to go half the remaining distance, and half the remaining distance, and you'll notice that the steps are getting smaller and smaller and smaller. All right, so this is an easy enough thing to model. We're going to label all of these distances, all of these steps. We're just going to assume that first the initial distance is some unit. I don't really care what it is, so let's call it 1. And then each next step after that is going to cut the distance in half. So before, with no steps, this is our initial position. This is after our first step. We have half the distance left. After our second step, we're going half of that half distance left, and now we have a quarter of the distance left. And now we're going to go half of that quarter distance left, and we have an eighth of a distance left, etc., etc., etc. And you can hopefully see by now that if we keep doing this forever and ever and ever, the only thing that's changing is the denominators, right? This makes sense. We're just multiplying by half every time. And so we know that when we multiply, you have 1 over some number in this case, and if we multiply that, I'll use a little dot, by a half, the numerators get multiplied together, and so the numerator is 1, and the denominator is just twice that number, right? So from a 16th, we go to a 32nd, and then to a 64th, and a 128th, etc., etc., etc. But what we'll notice is that for the distance to become 0, the only way that we can do this is to have a fraction that's going to be equal to 0, but any fraction that's equal to 0 is really just 0 over a number. And you'll notice that if we do this, we can't get that. It's impossible to get 0 divided by anything because our numerator is always going to be 1 times 1. Now, this is a pretty easy thought exercise to just do. Now, what we're going to notice is that the numbers get really small really fast, right? A 64th is a small fraction, and a 128th is really, really small. And then we could keep going, and doubling the size of that denominator is going to keep making these values really, really small. And what that means is that when we're here with our little tick mark, that's pretty close to our door, it's going to be really hard to actually notice that they're not at the door. Now, if you want to investigate more of Zeno's paradoxes, then a course like Real Analysis will give you the tools to really dig into the real number system and figure out how to make use of all this stuff and to kind of like solve these paradoxes. But for now, let's just use this as a way of modeling arbitrarily close. We're going to say that the student can get arbitrarily close to the door using this method because while the distance is never going to equal 0, the distance can get as small as we'd like. The student just has to keep taking more and more steps. So for every standard of what close means, for every definition of close, as long as that's not the distance has to be 0, they have to be the same position, as long as we have some distance greater than 0 that we're going to define as close, we can get close to the door by just continuing to take more and more and more steps until everybody is satisfied. Now that's kind of a wild thing to think about, but that's where we're at. So again, if we proceed here, then the distance will never actually be 0, but for anybody's definition of close, the student can always take enough steps to get close to the door. So this is what we mean by arbitrarily close. We're going to use these words, arbitrarily close, a decent amount as we start defining limits. So right now, we've not defined anything. We're just setting up some basics for understanding the kinds of thought process we're going to be using. Hopefully that's helpful, and in our next video, we're going to start diving into some actual definitions of limits to see where these concepts come into play.